I'm Xian from Princeton, and I'll be talking about sub-solar neutron stars. And before you throw me out, and I know Adam would want to, I'm glad he's not here right now, but let me just point out that last week there was a potential event with a moderate false alarm rate. It's very close, and the chirp mass is inferred to be lower than 0.87 solar masses. And this kind of mass is completely unachievable by normal neutron star and gravitation and black hole evolution channels. And it's more surprising, perhaps, is that it's already a second subsolar trigger we've seen in the past 3 months. And although the first one is very subthreshold. So my point is, maybe they're not real, but in anticipation of more of these triggers, it's quite timely to study how these subsolar compact objects may have formed. And so here I am to present one formation channel we come up with for subsolar neutron stars as one, and maybe currently, the only alternative to primordial black holes. And so to get to that, let me first begin with the story of how planets form. And so, no, I have not shown the wrong slide from a wrong conference, and it will become relevant. So when a star is born out of a cloud of gas, a lot of gas and dust collapses into a protoplanetary disk. Now, most planets form out of a slow core accretion channel where dust stick together to become asteroids, and then they accrete gas to slowly become, Neptunes or gas giants. But the story I tell today will focus on another channel called gravitational instability. It always happens when, in the outer part of the disk, the tumor Q parameter drops below unity. And if the disk is fast cooling, then, and it's also very thick or too compact, then it will tend to collapse into these fragments, and which happens to some very heavy protoplanetary disks. While the dust sticking channel is very slow and particular to the environment of protoplanetary disks, the disk instability channel is very quick and generally applies to any sorts of rotating disk system when the tumor Q parameter is below unity, whether around a supermassive black hole or a stellar mass black hole. So one system we can apply this to is the collapsar system. When a massive, rapidly rotating star collapses, it may form a black hole, newborn black hole, surrounded by very dense neutron-rich materials in the form of an accretion disk. This disk is suggested to power some long gamma ray bursts. But if we extend this disk, if it's dense enough, towards a few hundred Schwarzschild radius, it will also become gravitationally unstable. Despite a very high temperature and a high thermal velocity, these disks are just too dense, so the denominator is huge. And then if you extend to outer radii where omega drops below some threshold, then you can get gravitational unstable. So, the proof of concept is that in the outer region of this disk, we may expect them to fragment into clumps. And what will these clumps become? You may say, they become planetary systems, but not quite, because let's compare the typical properties of GI in planetary disk versus collapsar disk. So the host mass is similar in order of magnitude, but once you form things out of disk instability, the mass of clumps will be on the order of the local Jeans mass. And the local Jeans mass for these collapsar disks is on the order of 0.1 to 1 solar masses. So the mass compared to the host is relatively more equal compared to, gas giants in a planetary system. And also, if you look at the time scale, the distance, you will see that while the planets are stable on the time scale of giga-years, these things are formed so close to the central black hole that they will inspiral on the time scale of the gravitational inspiral time scale, which is 1,000 seconds. So this orbital system will be very short-lived planetary system analogs. And we haven't made this whole thing up. In fact, it has been long proposed, there's a historical motivation for this system, is that these fragments formed from gravitational instability in the outer parts of collapsar disks, if they stay as these puffy objects until they reach some tidal radius, they will get ripped apart once more and create these micro-TDE events and lead to delayed accretion episodes in long past the main collapsar accretion phase, which is during the outburst of the long gamma-ray burst. And so this may be invoked to explain some X-ray afterglows, X-ray flares in the afterglows of long gamma-ray bursts. But what if these puffy clumps themselves can become compact objects whose inspiral does not create micro TDEs, but gravitational waves? If we examine the nuclear reactions happening here, another intriguing possibility really appears, because this figure shows the electron fraction, YE, as a function of density and temperature for these kind of extreme environments, and this is governed by nuclear statistical equilibrium. At low densities, there are different regimes, but I just want to point out, if you go to very high density, that's when you form these collapses and fragments. The electron capture reaction will dominate to make the composition very, very neutron rich. So given enough time to contract and reduce their YE, any initial clump mass, even if subsolar, will reduce its YE, so its local Chandrasekhar mass becomes lower than one solar mass, and so gives them the possibility of evolving into low-mass neutron stars. So this is a qualitative picture. Demonstrated quantitatively, we carried out these 3D Schoenbach simulations using relevant equation of state tables and cooling functions, and here's a representative outcome. You're looking at top-down on a patch of the disk in the midplane, and then these things become unstable when it cools. Then it forms these density waves that break into clumps, structures. And inside these clumps, let me pause it here. So inside these clumps, you will see that the density becomes very high, and the YE dramatically drops compared to the surrounding materials. So at the end of the simulations, the clumps usually become too dense and involves off our equation of state tables. But before that, when we have some fidelity of on our simulations, if we compare the masses of these clumps, we'll see that on the x-axis, they're typically from 0.1 to 1 solar masses, so below solar mass. But on the y-axis, if we also plot the Chandrasekhar mass indicated by their average YE, we'll see that the YE is so low that the Chandrasekhar mass is even lower than the subsolar. So in this gray region, all these clumps have the potential of evolving into subsolar neutron stars. And so the formation of one of these objects is interesting enough and can create maybe gravitational signals once it inspirals inward. But it will be more interesting to have several of these, right? Low mass neutron stars and create multi-messenger possibilities. So neutron stars may form in binaries and eventually merge, producing very faint subsolar mass gravitational wave events. In terms of EM counterparts, they may be associated with a preceding long gamma-ray burst and a subsequent kilonova. And if the merger of binary neutron star does not kick the product out of the system, it may lead up to another louder gravitational event when the product inspirals into the central stellar mass black hole. And also, these gravitational waves will have very exotic waveforms that I will not go into details, but I'll be happy to discuss later. So there's this possibility we've proven, but what is the catch? Because our simulations are local, so we have to translate that into some global parameter space by mapping omega into some radius and also draw some contours of accretion rate. So the takeaway is that we need local accretion rate a bit higher than usual, larger than 1 solar mass per year, so the disk is dense enough to collapse. So that gives you some, can be inferred to be some fraction of collapsars capable of fragmentation. So if you want to calculate the rates of these things, you have to know about this kind of fraction, which itself is uncertain from some supernova physics. So I'll leave my summary slide here. Gravitational instability may form fragments in collapsars, and due to the electron capture activity here, the YE can drop dramatically. So the local Chandrasekhar mass becomes very low and very easy to surpass. And so this poses a channel for subsolar gravitational waves.
Thanks for the very novel talk. Let's see if we have some questions.
Thank you. Very interesting proposition. I was trying to look up, but I don't think I can actually find anywhere where there are people modeled what the size of a neutron star might be that has a mass of, let's say, 0.1 or 0.2 solar masses for reasonable equations of state, because I don't think people have typically thought that way. Have you thought about this? Like, is this what is the physical size of this neutron star, and given where you're forming it, how does it change, for example, the possibility of it being tidally disrupted much earlier than usual, etc.?
Yeah, I think it might be tidally disrupted, because it has a larger radius. But in our simulation, we do not let them actually evolve into neutron stars. We have a collapsar equation of state, which is below density 10 to the 12 or something. If they actually evolve into neutron stars, then then probably the equation of state will be in a kind of different regime from usual neutron stars, and they will have different implications. I think people have modeled, just take an isolated neutron stars and let it, going down to 0.1 solar masses if Y is very low. Then the conclusion is that in totally isolated environments, it's unstable on the weak interaction timescale, because then it will try to become an iron core of the same mass, because the binding energy is not negative enough. But that will be, if we form these very quickly in the collapsars, then they will be quick all the inspiral will be quick enough, so they will not disrupt due to these weak interactions before they inspiral into the center.
Okay, I think Ilya already asked my question, so I'll ask a different question, which is, you said that these objects form and then they're eaten up by the central object, like they inspiral into the central object.
Yes. So they get eaten.
So then the disk will get depleted.
Yes.
So does it keep getting replenished from?
Oh, yeah. So that is the historical reason why we're interested in this, even before gravitational waves, right? Okay. Because for gamma ray bursts, there's a long afterglow, and sometimes we see these flares in the afterglow. And this is one reason, one mechanism to replenish the disk after the main accretion channel, right? You retain some of the mass inside these clumps, and these clumps do not inspiral on the timescale of 1 second, which is the accretion timescale. And then only after the gravitational wave timescale, they get disrupted, and then a later accretion episode.
I can just say that I have modeled very low mass neutron stars. And so if you go to, say, even just half the solar mass, the radii can still be of order 10 kilometers for these things. If you go down to even lower solar masses, then it basically, the mass radius curve takes a sharp turn and can easily grow out to be 50 or 100 kilometers. So that still much, much more compact than like what an equivalent iron core would be, which then actually would give me pause thinking that this thing could somehow like puff out and expand, because it would have to fight the gravitational potential dramatically. So I think it would probably still sit there, but it could have a very, very large radius. And in fact, there have been some work recently saying that we might miss such objects with current gravitational wave searches because they don't take into account tides for these types.
Yeah, I think the template database is just right now incomplete for these objects.
Okay, let's do one last question, and why don't you come up and swap?
Johan Samsing, so all of the turbulence that you have in here and all the clumps that are forming, do they form some kind of fuzzy gravitational wave, background just happening around the merger? So if you like integrate all the power up that is happening around the merger, do you get like a significant, fuzzy background?
So when you say turbulent, are you referring to the disk turbulence?
The disk.
Yeah, the disk. So the disk turbulence generated by gravitational instability can reach of order alpha equals to 10%. And I don't know what that velocity translates to in terms of, and I think the key here is that the picture is you form these objects, and then very quickly on the same time scale where the disk is depleted. So it's after the disk depletion that these gravitational waves most likely is going to happen.
Okay.
Yeah.
Okay.
But I think the turbulence imprint on gravitational wave is another interesting subject, even happening in AGNs that I'm also very interested in. We should discuss it.
Great. Let's thank Yixian again. And Yixian, we need your, hold on. We need them.